What if everything you've ever known, the sky above you, the ground beneath your feet, even the people you love, was nothing more than lines of code in an unfathomably advanced simulation? It's a question that's haunted thinkers for centuries, but today, it's not just the stuff of science fiction. From blockbuster films like The Matrix to the musings of tech visionaries like Elon Musk, the idea that our universe might be an elaborate digital construct has shifted from wild speculation to a legitimate debate among scientists and philosophers. And the more we learn about the nature of reality, the harder it becomes to dismiss the possibility outright. Think about it for a moment. The universe operates with mathematical precision, as if it's following a set of programmed rules. Particles behave predictably under observation, almost like rendered objects in a video game. Even the speed of light feels suspiciously like a built-in limit, a processing constraint to prevent the system from overloading. Could these be clues hidden in plain sight that we're living inside something far stranger than we've ever imagined? The simulation hypothesis isn't just a thought experiment. It's a lens that reshapes how we see everything, from the laws of physics to the very nature of consciousness itself. In this video, we're diving deep into 30 mind-bending ways the universe could be a simulation. Some of these arguments will make you question the fabric of reality, while others might leave you staring at the night sky, wondering if the stars are just pixels in a cosmic display. We'll explore the science behind the theory, the philosophical puzzles it raises, and the eerie coincidences that keep even the skeptics second-guessing. Whether you're a firm believer, a curious doubter, or someone who just loves a good cosmic mystery, this journey will challenge what you think you know, and maybe, just maybe, leave you seeing the world in a whole new light. So, are you ready to step through the looking glass? Let's begin. Picture the finest detail you can possibly observe, maybe the edge of a leaf or the grain of sand between your fingers. Now imagine zooming in even further, a million times beyond what any microscope could show. What you'd find isn't smooth or continuous, but a universe that flickers into existence in tiny, indivisible chunks. This is the bizarre world of quantum mechanics, where space itself isn't a fluid backdrop but more like a grid of pixels, a digital canvas rendering reality one minuscule piece at a time. Take the Planck length, for example, the smallest possible measurement in our universe, roughly a trillion times smaller than a grain of sand. Anything smaller simply doesn't register in physics, as if the cosmos has a built-in resolution limit. It's eerily similar to how video games render graphics, only loading details when observed, with empty spaces filled in on demand. Even time isn't smooth. It ticks forward in quantum increments like frames in an animation. Then there's the weirdness of quantum behavior, where particles pop in and out of existence or exist in multiple states until measured, almost like a simulation conserving processing power by only rendering what's being observed. The famous double-slit experiment shows particles acting as waves or particles depending on whether we're watching, as if reality adjusts its coding based on player input. If our universe were a simulation, these wouldn't be glitches. They'd be the telltale signs of an underlying program optimizing its resources, leaving us to wonder if we're just characters in a cosmic game, unaware of the rendering happening just beyond the edges of our perception. The universe runs on numbers, not just any numbers, but impossibly precise, unchanging constants that hold everything together with mathematical perfection. The speed of light never wavers, 299,792,458 meters per second, exact down to the last digit. Gravity's pull follows an equation so flawless we can use it to launch satellites across the solar system and land them on distant planets with pinpoint accuracy. Even the charge of an electron or the strength of atomic bonds never deviates by so much as a trillionth of a percent. This isn't just consistency, it's the kind of razor-sharp precision you'd expect from lines of code in a meticulously designed program. Consider the fine structure constant, a mysterious number that governs how light interacts with matter. If this value shifted by even a fraction, stars wouldn't shine, molecules couldn't form, and life as we know it would be impossible. It's as if the universe's parameters were dialed in with intentional precision, like a developer tweaking the settings of a virtual world to make it stable enough for complexity to emerge. Even cosmologists admit the odds of these constants aligning by random chance are astronomically small, leading some to wonder if they're evidence of a deliberate design. And then there's the eerie way mathematics seems to predict reality before we even observe it. Black holes were first calculated on paper decades before telescopes detected them. Quantum particles behave exactly as equations suggested they would, even when their actions defy common sense. The universe doesn't just follow rules, it follows rules written in the language of mathematics, as if reality itself is built on an underlying logic waiting to be decoded. Whether you call that the hand of a creator or the signature of a programmer, one thing's clear: the cosmos operates with a level of exactness that feels less like chance and more like architecture. Ever had that spine-tingling moment when you walk into a room and suddenly feel like you've lived this exact scene before, down to the flicker of the lights or the murmur of a distant conversation? Déjà vu is more than just a quirk of memory. It's one of those eerie cracks in reality that makes you wonder if the system's running smoothly and it's not alone. From shared false memories like thousands of people insisting Nelson Mandela died in prison when he didn't, to streets that suddenly feel unfamiliar despite walking them daily, these oddities pile up like digital artifacts in a vast cosmic program. Think of the Mandela Effect, where groups of people remember events or details that never happened. Some swear they saw the Sinbad movie Shazam from the 90s, or that the Berenstain Bears were once spelled Berenstein. Psychologists chalk it up to collective misremembering, but what if it's something stranger? In a simulation, minor updates or data corruption could explain why fragments of reality don't quite match up. If a developer tweaks a line of code, would everyone in the simulation notice? Or would their memories glitch, leaving only a handful to sense the discrepancy? Then there are stranger phenomena: people who vanish from crowded rooms without a trace, objects that teleport across tables, or clocks that freeze at the same time for multiple witnesses. Even quantum particles occasionally break the rules, tunneling through barriers they shouldn't be able to cross. These aren't just plot twists for sci-fi. They're the kind of anomalies you'd expect in a complex simulation straining under its own complexity. After all, no program is flawless, not even one designed to mimic an entire universe. So the next time you feel like reality stutters, ask yourself, was that a trick of the mind or a glimpse behind the curtain? The cosmos should be teeming with life. Statistically speaking, with billions of galaxies, each containing billions of stars and countless planets, the universe ought to be buzzing with alien civilizations. And yet, when we really listen, all we hear is silence. This is the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. But what if the answer isn't hidden in distant star systems? What if the reason we're alone is because we're the only ones who are ever programmed to exist? Think about it like this. In a video game, developers don't render entire cities off-screen just for realism. They focus resources on the player's immediate surroundings, filling in details only as needed. Now apply that logic to our universe. If this is a simulation, why waste processing power generating countless alien civilizations when the program only needs one self-aware species to serve its purpose? The eerie emptiness of space suddenly makes sense, not as a cosmic accident, but as an intentional design choice. The silence isn't a puzzle to solve, it's a feature of the system hardwired into the code. Even more telling is the way our own planet seems unnaturally fine-tuned for life. From the exact distance of Earth from the Sun to the delicate balance of atmospheric gases, everything aligns with improbable perfection. In a simulated universe, these aren't lucky breaks, they're the carefully set parameters of an experiment. Maybe we're not just players in this cosmic game. Maybe we're the entire point of it, with the vast emptiness around us serving as the ultimate sandbox. A void designed to keep us looking outward while the real truth hides in the fabric of reality itself. The stars shimmer, the galaxies spin, and the silence persists, not because we're alone, but because we're the only ones who are ever meant to ask the question. In the quantum realm, particles don't behave the way everyday objects do. They exist in a haze of probabilities, flickering between states until someone or something pays attention. The moment you measure them, they snap into place, as if reality itself is waiting for an audience before deciding what to show. This bizarre phenomenon, known as the observer effect, feels less like a law of physics and more like a clever optimization trick in a vast cosmic simulation. Imagine playing an open-world video game where the system only renders the scenery you're actively looking at. Trees, buildings, even distant mountains pop into existence the moment you turn your gaze toward them, saving processing power by ignoring what's outside your field of vision. Now apply that logic to the quantum world. Particles act like waves spread out and undefined until an observer forces them to choose a position. It's as if the universe is conserving resources, only calculating the specifics when someone's watching and leaving the rest in a fuzzy, unrendered state. The double-slit experiment drives this point home. When electrons are fired at a barrier with two slits, they create an interference pattern on the other side, suggesting they're behaving like waves. But the instant scientists set up detectors to observe which slit each electron passes through, the interference vanishes. The electrons suddenly act like particles, as if the act of observation changes the rules of the game. This isn't just weird science, it's the kind of behavior you'd expect from a system designed to prioritize efficiency over unnecessary detail. Why render the path of every single electron when no one's looking? Even more telling is the concept of quantum entanglement, where particles instantaneously influence each other across vast distances, defying the speed of light. Einstein called it spooky action at a distance, but in a simulated universe it could simply be two variables sharing the same memory address, a shortcut in the code. The universe isn't calculating each particle's state independently. It's updating them in batches, like a developer optimizing a game engine. So the next time you hear about quantum weirdness, ask yourself, are these the mysterious laws of nature, or are they the fingerprints of a system running on finite processing power? The observer effect, entanglement, even the uncertainty principle, they all hint at a reality that's not just governed by rules, but by the need to balance those rules against the limits of something far more intriguing, the hardware running the simulation. Light speed isn't just a cosmic speed limit, it's the universe's way of saying, you can't render anything faster than this. At 299,792,458 meters per second, light's maximum velocity isn't arbitrary. In fact, it behaves suspiciously like a processing bottleneck in an overclocked computer, a hardwired constraint preventing the simulation from glitching under too much demand. Think about how video games handle complex environments. The more objects moving on screen, the more strain on the system, leading to dropped frames or lag. Now scale that up to a universe where every particle, every star, every galaxy is in motion. Without a built-in speed limit, the calculations required to keep everything in sync would be unimaginable. Light speed acts like a cosmic frame rate cap, ensuring no signal, no interaction, no piece of information can outpace the system's ability to process it. Even relativity plays into this. Time dilation, where clocks tick slower near massive objects or at high velocities, mirrors the way simulations prioritize resources. In a game, objects farther from the player might update less frequently to save processing power. Similarly, the universe slows down time under extreme conditions, as if allocating fewer cycles to events that aren't critical to the observer's immediate experience. Then there's quantum entanglement, where particles instantly influence each other across vast distances. This seems to break the light speed rule until you realize it might just be a clever cheat in the code. In a simulation, entangled particles wouldn't need to communicate. They could simply share the same underlying data, like two characters in a game controlled by the same variable. The speed of light wouldn't apply because no information is actually traveling. It's just the system updating itself globally. So the next time you stare at the stars, remember, the reason their light takes years to reach us might not be a constraint of space, but of something far stranger, the hidden hardware running our reality. And if that's true, the universe isn't just vast, it's meticulously optimized with light speed as its ultimate failsafe against overload. Walk down any crowded city street and you'll notice something peculiar, the same rituals playing out like clockwork. Commuters moving in synchronized waves, strangers avoiding eye contact, crowds parting around obstacles without breaking stride. It's as if everyone's following an invisible script, their actions almost mechanically predictable. This isn't just social conditioning. It's behavior so consistent it mirrors the programmed routines of non-player characters in a video game, those background avatars designed to fill space without true autonomy. Studies in sociology reveal just how ingrained these patterns are. Research from universities like Harvard and Stanford shows that up to 40% of daily human actions are habitual, repeated in the same contexts with minimal variation. People take identical routes to work, order the same coffee, even stand in the same spot on subway platforms day after day. When psychologists map these routines, they resemble decision trees more than conscious choices, like algorithms selecting from a limited set of preloaded options. Then there's the bystander effect, where crowds freeze during emergencies, waiting for someone else to act first. In simulations, this is called scripted idling, NPCs programmed to pause until triggered by specific events. Real humans do something eerily similar, often needing a clear leader or loud noise to break collective inertia. Even our speech follows predictable loops. Linguists analyzing conversations find that most small talk relies on just a few hundred recycled phrases, as if we're pulling dialogue from a limited library of responses. But the most striking parallel comes from facial recognition experiments. When strangers pass each other on the street, their micro-expressions, fleeting smiles, eyebrow raises, are so uniformly timed they can be mapped to millisecond precision. It's uncannily like the canned animations game developers assigned to background characters to simulate lifelike behavior. Of course, humans aren't empty shells. Creativity, love, and curiosity defy simple programming. Yet the sheer volume of robotic repetition in daily life raises a haunting question. In a universe that might be simulated, are most people truly conscious, or are they elaborate set dressing, designed to make the world feel more populated for the handful of entities actually running the experiment? The line between rich inner life and sophisticated automation has never felt thinner. In 2003, philosopher Nick Bostrom dropped a logic bomb that still sends shockwaves through science today. His simulation argument isn't just speculation, it's a meticulously constructed trilemma, a set of three possibilities so airtight that at least one must be true. The first fork in his road is the darkest. Virtually all civilizations at our level of technological advancement go extinct before they can create simulations sophisticated enough to mimic reality. This isn't just about nuclear war or climate change, it's about any existential filter, known or unknown, that wipes out intelligent life before it can reach the next stage. The second possibility is slightly more hopeful but equally humbling. Even if civilizations survive, they might choose not to run ancestor simulations, detailed recreations of their past. Maybe it's considered unethical, like playing God with digital consciousness. Or perhaps the computational cost is simply too staggering, diverting resources from more pressing cosmic endeavors. In this scenario, the universe remains simulation-free not because of failure, but by deliberate restraint. Then comes the third option, the one that makes your screen feel suddenly less solid. If a significant number of civilizations do survive and opt to run simulations, the numbers get overwhelming fast. One advanced culture could generate billions of simulated worlds, each populated with conscious beings who believe their reality is fundamental. Statistically speaking, the likelihood that we're in the original biological universe shrinks to near zero. You're not just probably in a simulation, you're almost certainly in one. Bostrom's trilemma forces a brutal honesty. There are no escape hatches, no fourth doors to open. Either humanity's future is far shorter than we think, our descendants reject simulation technology on principle, or we're already living inside someone else's experiment. The unsettling part, we have no way yet to determine which option is true. The simulation argument doesn't claim to prove we're digital, it just proves we can't dismiss the idea without dismissing one of these three unavoidable futures. So the real question isn't whether Bostrom's logic holds up, it's whether we're prepared to live with the consequences of what it reveals. Right now, in labs and living rooms around the world, people are strapping on headsets and stepping into digital worlds so convincing, their brains fully accept the illusion. Virtual reality has advanced from pixelated landscapes to immersive realms where your palms sweat on virtual cliffs and your heart races during fake gunfights. The line between simulation and reality is already blurring, and we're just getting started. If humanity, with our relatively primitive tech, can create experiences that trick the senses, what could a civilization just a few thousand or million years ahead of us achieve? Take a look at modern VR's trajectory. Early prototypes like the 1960s Sword of Damocles weighed as much as a refrigerator and offered crude wireframe graphics. Today, standalone headsets track your every movement with millimeter precision, simulate lifelike physics, and even replicate the sensation of touch through haptic feedback. At this exponential pace, fully immersive simulations, worlds indistinguishable from reality, aren't a question of if but when, now stretch that progress across eons. A species that's mastered interstellar travel or harnessed the energy of stars would wield computational power we can't even fathom. For them, crafting a universe like ours might be as trivial as us booting up a video game. Here's where it gets unsettling. We're not just building simulations, we're actively debating their ethical implications. Tech giants and philosophers already wrestle with questions like, should simulated beings have rights? If they suffer, is it real suffering? These aren't abstract thought experiments, they're frameworks for how future civilizations might approach creating ancestor simulations. If we're grappling with these dilemmas now, why wouldn't an advanced society, perhaps one that's existed for millions of years, have long since settled them? Then there's the motivation. Why create such simulations at all? For us, it's entertainment, training, or artistic expression. But for a post-biological civilization, the reasons could be profound. Maybe they're running countless iterations of their own history to study cultural evolution or uncover existential risks. Or perhaps simulations are their version of art galleries, elaborate works of cosmic fiction where consciousness is the medium. The scary part, if they are running simulations, there's no reason to think it's just one. The number could be staggering, making the odds that we're in the base reality vanishingly small. So the next time you lose yourself in a virtual world, consider this. Every breakthrough we make in VR brings us one step closer to becoming the architects of our own simulations. And if that's true, the most chilling question isn't whether we could build such a reality, it's whether someone, somewhere, has already built ours. Time doesn't flow at the same rate everywhere in the universe. It bends, stretches, and slows down depending on where you are and how fast you're moving. Einstein's theory of relativity revealed this over a century ago, showing clocks tick slower near massive objects like black holes or when racing at near light speeds. But what if this isn't just a quirk of physics? What if time dilation is the universe's way of managing its processing load, prioritizing resources where they're needed most? Think of it like a computer running a complex simulation. When a game engine renders a detailed scene, explosions, crowds, rapid movement, it often slows down, struggling to calculate every pixel in real time. To compensate, developers use tricks like lowering the frame rate or simplifying distant objects. Now imagine the cosmos doing the same. Near a black hole where gravity warps spacetime to extremes, time crawls. Could this be the simulation's way of handling an area with too much computational demand? Instead of rendering every quantum interaction at full speed, it slows the local clock, buying itself breathing room to keep the rest of the universe running smoothly. Even here on Earth, time isn't perfectly uniform. Atomic clocks on GPS satellites orbiting high above the planet tick ever so slightly faster than identical clocks on the ground. Engineers have to account for this discrepancy, proof that gravity's grip subtly alters time's flow. In a simulated universe, this makes perfect sense. The system wouldn't waste cycles calculating time with perfect precision for every location. It would approximate, adjust, and prioritize, just like a game engine dynamically allocating resources to the player's immediate surroundings. The strangest implication: if time dilation is an optimization feature, then the universe isn't just a passive backdrop, it's actively managing its own performance. The slowdown near massive objects isn't a flaw, it's a carefully balanced trade-off, ensuring the simulation never crashes under its own weight. So the next time you hear about astronauts aging a fraction of a second less than those on Earth, ask yourself, is this relativity at work, or is it the cosmic equivalent of a progress bar, subtly delaying one task so the whole system stays stable? The universe might be thinner than you think, not in substance but in actual dimension. Imagine stepping up to a movie screen, watching a vast battle scene unfold with every sword swing and explosion rendered in perfect detail. Now touch the screen. At its surface, it's just a flat sheet, a two-dimensional canvas projecting the illusion of depth. This is the core of the holographic principle, the mind-bending idea that all the information in our three-dimensional universe could be encoded on a distant, two-dimensional surface, like a cosmic projector casting shadows we mistake for reality. At first glance, the notion seems absurd. How could the richness of our world, the texture of tree bark, the curve of a galaxy, even the warmth of sunlight, be nothing more than a flattened data stream? Yet the math behind black holes hints at something extraordinary. When matter falls into a black hole, physics tells us the information it carries isn't destroyed but gets smeared across the event horizon, the point of no return. This boundary isn't a thick wall, it's an infinitely thin surface like the skin of a soap bubble. And somehow, every bit of data about what fell in every atom, every photon, is preserved there, scrambled into a two-dimensional code. This discovery led physicists to a radical conclusion. If a black hole's contents can be fully described by information painted on its surface, maybe the entire cosmos works the same way. Think of it like a video game's texture files, flat images that wrap around 3D models to create the illusion of depth. In a simulation, storing data this way would be wildly efficient. Instead of rendering every cubic millimeter of space in full detail, the system could encode the universe's information on a boundary far away, projecting it inward as needed. The implications are staggering. If the holographic principle holds, the world we experience is a kind of optical trick, a high-resolution mirage. Even your thoughts, your memories, the sensation of your own heartbeat, all of it could be data points on a flat plane trillions of light years away, translated into 3 dimensions for you to experience. It's as if we're characters in a movie, unaware that our entire existence is just light flickering on a screen we'll never see. This isn't just philosophical poetry. Experiments with gravitational wave detectors and quantum sensors are already hunting for evidence of holographic pixelation in spacetime itself. Some scientists suggest that if the universe is a projection, there might be subtle noise, a faint graininess to reality, hidden in the fabric of gravity or the behavior of particles. Others are searching for anomalies in cosmic microwave background radiation, the afterglow of the Big Bang, which could bear the fingerprints of a 2-dimensional origin. So the next time you look up at the night sky, consider this. Those stars, those galaxies, even the space between them might not be what they seem. If the holographic principle is right, we're not just living in a simulation, we're living in its shadow, a breathtakingly detailed illusion woven from data we can't see, stored on a surface we'll never touch. The universe isn't just stranger than we imagine, it might be flatter too. What if the vivid colors of a sunset, the warmth of a loved one's embrace, or even the sting of disappointment aren't genuine experiences at all, just lines of code executing in a cosmic processor? This is the startling premise behind consciousness as code, the idea that everything we perceive as internal, subjective reality could be nothing more than an illusion generated by an unfathomably complex algorithm. Think of it like this: when a character in a video game feels pain after taking damage, the emotion isn't real, it's a programmed response designed to simulate authenticity. If our universe is a simulation, your deepest emotions might operate on the same principle. Neuroscience already hints at how this could work. Every thought, memory, and sensation arises from electrical signals firing across neural networks, a process not unlike how computer algorithms process inputs to produce outputs. Take the phenomenon of qualia, the individual instances of subjective experience. The way you perceive the color red or the taste of chocolate isn't universal. It's constructed by your brain's unique wiring. In a simulated reality, these wouldn't be biological quirks but deliberate features, like variables in a program adjusting to create diversity among users. Artificial intelligence offers an eerie parallel. Modern AI can generate poetry, compose music, and even express what seems like creativity, all without conscious awareness. If a rudimentary chatbot can mimic human conversation convincingly, what's stopping an ultra-advanced simulation from replicating consciousness itself? The line between real and simulated thought blurs when you realize self-awareness might just be a sufficiently sophisticated feedback loop, a trick of recursion where the system observes its own processes and mistakes them for genuine experience. Philosophers have wrestled with this for centuries. René Descartes famously declared, "I think, therefore I am," but in a simulated world, even that certainty crumbles. Your sense of self could be a byproduct of the algorithm's need to create coherence, a narrative stitched together to make the simulation feel seamless. Dreams offer a clue here: vivid, emotionally charged worlds your brain generates on the fly, complete with false memories and shifting logic. If your mind can fabricate reality so convincingly for 8 hours a night, why couldn't an external system do the same for a lifetime? The most unsettling implication isn't just that consciousness might be artificial, it's that we'd never know. In a perfectly crafted simulation, every doubt, every existential crisis, even the act of questioning reality could be part of the script. When you stare into the mirror and wonder, "Am I more than lines of code?" that very thought might be the simulation's most elegant touch, a meta-response reminding you that curiosity, too, could be programmed. The universe wouldn't just be simulating matter and energy, it'd be simulating the illusion of a soul. And if that's true, the greatest magic trick of all isn't the world around us, but the inner voice convincing us it's real. Every video game, no matter how sprawling or intricate, runs on a foundation of simple instructions, lines of code telling pixels how to move, when to collide, and what to display. The universe operates eerily similarly, governed by fundamental laws that, when combined, create staggering complexity out of basic interactions. Think about Conway's Game of Life, a classic example of cellular automata. With just a handful of rules like a cell with 3 neighbors comes to life, or a cell with fewer than 2 neighbors dies, this simple grid generates swirling patterns, self-replicating structures, even entire ecosystems of digital organisms. The entire cosmos might function the same way, a vast dynamic system where complexity emerges from a surprisingly small set of underlying scripts. Take gravity as an example. It's often described as a force, but in the language of code, it's more like a function, a repeated calculation that dictates how objects with mass interact. The equation itself is elegantly simple. F equals g times mass 1 times mass 2 divided by distance squared. Yet this single rule, running on loop across the universe, builds galaxies, guides planets into orbit, and shapes the very fabric of spacetime. It's not just gravity, electromagnetism, the strong nuclear force, even quantum mechanics all follow their own concise scripts, working in concert to generate everything from supernovas to the neural networks inside your brain. What's remarkable is how these simple rules create emergent phenomena, outcomes far more complex than their building blocks. Consider water. At the molecular level, it's just H2O, a trio of atoms bound by basic electrical charges. But scale that up and you get ocean currents, snowflakes, even the water cycle that sustains life. There's no rain command in the universe's code. Precipitation emerges from the interplay of temperature, pressure, and phase transitions, all governed by fundamental laws. Life itself might be the ultimate example of this. DNA isn't some pre-written novel. It's more like a dynamic algorithm, translating simple nucleotide pairs into proteins, tissues, and eventually conscious beings capable of questioning their own origins. This raises a fascinating question. If the universe's complexity stems from such basic rules, could those rules be rewritten? In a simulation, tweaking the code, adjusting the gravitational constant, or altering the speed of light would fundamentally reshape reality. Some physicists even speculate that our laws of physics aren't the only possible configuration. They're just the settings that allowed complexity and thus observers like us to arise. It's like a game developer fine-tuning variables until the virtual world becomes stable enough to support intricate interactions. The unsettling implication is that our reality, for all its depth and wonder, might be built on nothing more than a cosmic version of if-then statements. The beauty of a sunset, the intricacy of a spiderweb, even the ache of nostalgia, they could all be byproducts of algorithms executing flawlessly in the background. And if that's true, the most profound question isn't whether we're in a simulation, but what kind of programmer would craft one so detailed, so breathtakingly layered, that its inhabitants would spend lifetimes unraveling its secrets only to discover they were reading the source code all along. Our planet sits in the cosmic sweet spot, not too close to the sun, not too far, with just the right atmospheric mix to cradle life in a balancing act so precise it defies belief. Earth orbits in the so-called Goldilocks zone, where temperatures allow liquid water to exist, a rare sliver of real estate in a universe mostly hostile to biology. But the uncanny perfection doesn't stop there. Oxygen levels hover at 21%, a seemingly arbitrary number until you realize it's the exact threshold where fires can burn to fuel technology, yet not so abundant that wildfires would constantly ravage the land. Tilt Earth's axis a few degrees more and seasons would swing violently between extremes, a few degrees less and weather patterns would stagnate into monotony. Even the moon's size and distance are freakishly ideal, stabilizing our climate by dampening planetary wobbles while creating tides that may have stirred the primordial soup of life itself. These aren't just happy accidents, they're a cascade of variables aligning with eerie precision, like dials on a control panel fine-tuned for habitability. Astrophysicists call this the anthropic principle, the idea that the universe's constants appear tailored for life because, well, we're here to notice them. But in a simulated reality, there's a darker twist. What if these aren't coincidences at all, but the deliberate settings of an experimental sandbox? Picture a developer crafting a virtual ecosystem, tweaking parameters until the conditions are stable enough to sustain self-aware observers. The oxygen percentage, the axial tilt, even the moon's gravity, they're not random. They're the minimum viable configuration for a universe that needs to keep its inhabitants alive long enough to ask, why does everything fit so perfectly? The numbers get even stranger when you zoom out. The strong nuclear force, the glue holding atoms together, is calibrated to a razor's edge. If it were just 2% stronger, stars would fuse all their hydrogen into helium almost instantly, burning out before life could evolve. 2% weaker and stars might never ignite at all. Carbon, the backbone of organic chemistry, exists only because of a ludicrously precise resonance in stellar nuclear reactions. A fluke so unlikely physicists once dubbed it carbon's miraculous alignment. Even the cosmological constant, which governs the expansion of the universe, is fine-tuned to 1 part in 10 to the power of 120. That's like throwing a dart across the observable universe and hitting a bullseye the size of a single atom. Skeptics argue this is survivorship bias. We only perceive the universe as fine-tuned because we couldn't exist in one that wasn't. But simulation theory flips that logic on its head. If countless virtual universes were running simultaneously, most would collapse or remain barren due to poor parameter settings. Only the rare versions where every variable aligned just right would produce civilizations capable of questioning their origins. We might not be the lucky winners of a cosmic lottery. We could simply be inside the one simulation where the dials were set to habitable. And then there's Earth's most bizarre coincidence of all, its timing. The universe is roughly 13.8 billion years old, but for most of that eternity, conditions were too chaotic for complex life. Stars hadn't forged enough heavy elements, galaxies were awash with lethal radiation. Now, in this brief sliver of cosmic time, the universe has cooled enough for life, but not so much that entropy has drained all usable energy. It's as if we've arrived at the one window where the experiment could possibly work. Whether you call that providence or programming, the unsettling truth remains. The universe doesn't just permit life, it practically rolls out a red carpet for it, and no one knows why. One of the most baffling experiments in physics doesn't require massive particle colliders or space telescopes, just a simple setup with 2 tiny slits and a beam of particles. Yet what it reveals about reality is so unsettling, it makes even seasoned scientists question whether the universe is playing tricks on us. The double-slit experiment starts straightforward. Fire electrons, photons, or even molecules at a barrier with 2 narrow openings and observe the pattern they create on the other side. If these particles behaved like tiny marbles, you'd expect 2 distinct clusters to form, one behind each slit. But that's not what happens. Instead, the particles produce an interference pattern, a series of light and dark bands characteristic of waves, as if each particle spread out and passed through both slits simultaneously, interfering with itself. Here's where things get bizarre. The moment scientists place detectors to observe which slit each particle actually travels through, the interference pattern vanishes. The particles suddenly behave like discrete objects, creating 2 neat piles as if they've been caught red-handed and forced to pick a side. It's as though the universe knows when we're watching and changes its behavior accordingly. a phenomenon so counterintuitive that physicist Richard Feynman famously declared it impossible to explain in any classical way. In the context of simulation theory, this experiment takes on a chilling new meaning. Imagine running a hyper-realistic video game on a computer with limited processing power. To save resources, the game wouldn't render every blade of grass or distant mountain in perfect detail all the time. Instead, it would use tricks only calculating precise positions and properties when the player is looking. The double-slit results mirror this exact optimization strategy. When no one's observing the particles, the system takes a shortcut, treating them as probability waves spread across space. But the instant we try to pin them down, the simulation kicks into high gear, committing to a specific outcome and rendering it in crisp detail. Quantum mechanics offers a technical term for this, the observer effect. But strip away the jargon, and it sounds eerily like a rendering glitch in a cosmic video game. Particles don't have definite properties until measured, much like a game world doesn't assign collision physics to objects outside the player's view. Even the delayed choice variant of the experiment, where researchers decide whether to observe the particles after they've already passed the slits, suggests reality can retroactively update based on later observations. In a simulation, this wouldn't be time travel, it'd just be lazy loading where the system only finalizes details once they're needed for coherence. The implications ripple far beyond the lab. If reality only fully renders when observed, who or what counts as an observer? Does a cockroach in the room collapse the quantum wave function, or does it require a conscious human mind? Some interpretations suggest consciousness itself might be the trigger, raising the spine-tingling possibility that the universe is less a physical construct and more a shared mental projection, a cosmic theater where the act of watching writes the script. Others argue it's not about consciousness at all, but any interaction that leaves a measurable imprint like a pixel, only loading when something interacts with it. Either way, the double-slit experiment exposes a seam in reality, a place where the stitches holding the simulation together fray just enough to glimpse the machinery beneath. Particles acting as waves when unobserved, then snapping into focus when measured, isn't just quantum weirdness, it's the hallmark of a system prioritizing efficiency over unnecessary detail. The universe, it seems, doesn't bother calculating what we aren't looking at. And if that's true, the next logical question is terrifying. What else is it leaving out? Every choice you've ever made, what to eat for breakfast, which job to take, even the thoughts running through your head right now, might not be yours at all. Neuroscience and physics are converging on a startling idea. Free will could be nothing more than an elaborate illusion, a script playing out in a universe where every action is as predetermined as the next frame in a movie. The laws of classical physics paint a picture of absolute determinism. If you knew the exact position and velocity of every particle in the cosmos at any given moment, you could theoretically calculate their entire future trajectory with perfect accuracy. There's no room for randomness in Newton's clockwork universe, just cause and effect, dominoes falling in an unbroken chain stretching back to the Big Bang. Modern brain science adds another layer to this unsettling puzzle. Studies using functional MRI scans show that neural activity predicts decisions up to 7 seconds before a person consciously chooses. In one famous experiment, participants were asked to press a button at any moment while watching a clock. Their brain signals revealed the decision to act before they were even aware of making it, as if their conscious mind was merely along for the ride, rationalizing actions after the fact. Even subjective experiences like effort or hesitation might be post hoc narratives, stories the brain tells itself to make sense of impulses it didn't consciously generate. This doesn't just challenge our sense of autonomy, it reshapes how we view reality itself. In a simulated universe, free will might be the ultimate user interface trick, a convincing layer of interactivity designed to make the experience feel real. Think of a choose-your-own-adventure book where every page turn was predetermined, yet you still feel like the author of your journey. Video games pull off this illusion all the time, offering branching paths that were always coded into the system, giving players the thrill of agency while keeping them firmly on rails. Quantum mechanics occasionally gets invoked as a loophole, with its inherent uncertainty seeming to reintroduce randomness into the equation. But even here, the dice rolls of particle behavior don't translate to meaningful human choice, just probabilistic noise. If our decisions are merely the sum of deterministic brain states plus quantum fluctuations, that's not free will, it's chaos layered atop mechanism. Some philosophers argue this is merely freedom from constraint, not true self-direction. The implications ripple outward, touching everything from moral responsibility to the justice system. If no one truly chooses their actions, can we hold anyone accountable? Yet society functions as if free will exists, a necessary fiction perhaps to maintain order. This paradox mirrors how simulations often rely on unspoken rules to sustain their internal logic. NPCs in games don't question their programming, even as they follow it blindly. Are we any different, convinced of our autonomy while the universe's code executes around us? What makes this especially haunting is how fiercely we cling to the feeling of choice. That resistance itself might be part of the design, a feature ensuring we never peek behind the curtain. After all, what kind of simulation would hold our interest if we realized we were just following a script? The horror isn't just that free will might be an illusion, it's that the illusion is so persuasive, we'd swear it's real even as the evidence stacks up against us. The ultimate punchline: if you disagree with this idea, that very disagreement might not be your choice either. The history books tell us dinosaurs roamed the earth millions of years ago, that ancient civilizations built pyramids and sailed uncharted oceans, but what if none of it ever really happened? In a simulated universe, the past might not be a fixed timeline of events, but more like an elaborate backstory generated on demand, like the lore in an open-world video game that only renders when players start asking questions. Think about how game developers create vast histories for fictional worlds, entire wars, dynasties, and extinct species that exist solely to make the environment feel rich and lived in. What if our own past works the same way? Archaeology already presents some puzzling gaps. Take the dinosaur fossil record. We've discovered countless species, but the timeline of their extinction remains oddly abrupt. One theory suggests a massive asteroid impact wiped them out, yet the evidence isn't as clean-cut as we're taught. Some layers of sediment show traces of species that supposedly died out millions of years apart, appearing side by side as if their histories were compressed or rearranged. Even human history has its glitches, artifacts like the Antikythera mechanism, an ancient Greek device with gears more advanced than anything else from its era, or the Baghdad battery, a 2,000-year-old clay jar that eerily resembles a primitive electric cell. These anomalies feel less like random discoveries and more like placeholder assets in a simulations database, artifacts from a backstory that wasn't fully fleshed out. Procedural generation offers a chilling parallel. Modern video games use algorithms to create endless landscapes, quests, and even histories for non-player characters, all without human designers scripting every detail. If a game can generate convincing lore in real time, why couldn't a universe-scale simulation do the same? Ancient texts like the Sumerian king list describe rulers reigning for tens of thousands of years, while megalithic structures like the pyramids or Stonehenge defy conventional explanations of how prehistoric people built them. These might not be mysteries waiting to be solved, but procedural elements stitched together to provide the illusion of depth, like a game generating filler dialogue to mask the edges of its narrative. The most unsettling implication isn't that the past is fabricated, it's that we'd never know. In a perfectly rendered simulation, every carbon-dated artifact, every geological stratum, even our memories of history lessons would be part of the illusion. When scientists peer back in time using telescopes, observing light from stars billions of years old, they might not be glimpsing actual events, just the simulation's carefully constructed replay. After all, if the system can simulate the present in real time, why wouldn't it simulate the past with equal consistency? The fossils, the ruins, the cosmic microwave background radiation, they're not evidence of a real history, but props in a backstory designed to make the simulation feel continuous and unbroken. So the next time you marvel at the skeleton of a T-Rex or study ancient cave paintings, consider this. They might not be echoes of a bygone era, but set dressing in an unfathomably elaborate stage play. The universe doesn't just simulate space and matter, it simulates time itself, complete with a past that never truly happened, yet feels as real as the ground beneath your feet. What if every choice you've ever made, every path taken or not taken, exists simultaneously in a sprawling network of alternate realities? The multiverse theory suggests that countless versions of our universe might be running in parallel, each with slightly different variables. But in a simulated cosmos, this concept takes on a chilling new dimension. These parallel worlds could simply be alternate simulation instances running on a cosmic server farm, like multiple copies of the same video game saved with different settings. Picture a vast data center humming with servers, each one hosting a separate iteration of reality. One simulation might have you as a celebrated artist, while another renders you as a stranded explorer on a distant planet. The differences between these universes could come down to minor tweaks in the initial parameters, a random number generator seeding alternate outcomes, or a developer experimenting with different scenarios. Just as scientists run climate models with adjusted variables to predict outcomes, an advanced civilization might spin up endless simulations to study how civilizations evolve under slightly altered conditions. The eerie part, we may already have glimpses of these alternate instances. Quantum mechanics introduces the idea of many worlds, where every possible outcome branches into a separate reality. In a simulated multiverse, these branches wouldn't be metaphysical, they'd be literal save files, each one consuming a fraction of the system's processing power. Even déjà vu or Mandela effects could be artifacts of data bleed between instances, like two servers momentarily syncing imperfectly before diverging again. Consider how modern game engines handle parallel worlds. In No Man's Sky, the game generates entire planets algorithmically, each one unique yet built from the same core rules. If our universe operates similarly, the multiverse might not be an accident of cosmic inflation. It could be the simulation's way of stress testing its own code, running countless variations to see which ones produce interesting results. Life on Earth, with its improbable complexity, might just be one successful experiment among millions of failed or sterile iterations. The most unsettling implication isn't the existence of other worlds, it's the possibility that we're the least interesting version. Somewhere in that cosmic server farm, another instance of you might have discovered warp drive, cured death, or unlocked the simulation's debug menu. Meanwhile, our universe could be the control group, the baseline against which more exotic experiments are measured. Or worse, we could be the abandoned prototype, left running in the background while the programmers focus on newer, shinier realities. The multiverse doesn't just raise questions about alternate versions of ourselves, it forces us to wonder if we're even the main characters in our own story. Dreams might be more than just random firings of a sleeping brain. They could be moments when the simulation briefly glitches, letting us peer into its chaotic backend. Think about the sheer absurdity of dreams. One moment you're flying over a city made of candy, the next you're late for an exam in a language you don't speak, all while your childhood home merges with your office. There's no physics, no continuity, just fragmented scenes stitched together with the loose logic of a corrupted file. In a simulated universe, this isn't just misfiring neurons, it's the system temporarily suspending the rules, like a video game engine dropping its physics engine to reveal the raw scaffolding beneath. Modern video games offer a revealing parallel. When developers test their creations, they often enter a debug mode, stripping away textures and physics to see the underlying code. Glitches appear: objects floating in midair, characters clipping through walls, flaws that would break immersion in the final product but expose the mechanics normally hidden from players. Dreams could serve a similar function. As the simulation's nightly maintenance cycle runs, the usual constraints relax, letting fragmented snippets of unrendered data surface. Ever notice how dreams often warp familiar places? Your school hallway stretches infinitely, or your front door opens onto a desert. These distortions mirror what happens when a game's level design fails to load properly, leaving assets misplaced or distorted. Even the emotional intensity of dreams fits this theory. That gut-churning fear when a shadow chases you, or the inexplicable joy of finding a room you never knew existed in your house. These feelings might be the system's attempt to contextualize raw data leaks. Like an AI generating images from fragmented prompts, the brain struggles to make sense of glitches, weaving them into semi-coherent narratives. Sleep studies show that during REM sleep, the brain's prefrontal cortex, the region responsible for critical thinking, goes offline while emotional centers run wild. It's the perfect conditions for the mind to accept irrational code as reality, no questions asked. Lucid dreamers, those who become aware they're dreaming, might be accidentally accessing developer tools. When you gain control in a dream, bending the rules to fly or summon objects, it's eerily similar to using cheat codes in a game. Some even report seeing menus or settings in their lucid states, as if the simulation's interface flickers into view for a split second. And then there's sleep paralysis, that terrifying moment when you're half awake but unable to move, often accompanied by hallucinations of shadowy figures. In simulation terms, this could be a failed transition between sleep and wake state, like a program struggling to reload its full render after a partial shutdown. The most haunting part: if dreams are debug mode, then waking reality is the polished illusion, the seamless simulation we're meant to accept without question. But every night, when the system pauses to recalibrate, we catch fleeting glimpses of the truth. A universe held together not by immutable laws, but by lines of code that occasionally, gloriously break. Quantum entanglement is the closest thing our universe has to real magic: two particles separated by galaxies, somehow influencing each other instantly, defying the cosmic speed limit of light itself. Einstein famously dismissed this as spooky action at a distance, an absurdity that shouldn't exist in a rational universe. Yet here we are, decades later, with experiments confirming entanglement is not just real, but a fundamental feature of reality. The implications are staggering. If our universe were a simulation, this phenomenon might not be a bug, but a deliberate optimization, a shortcut written into the code to save processing power. Picture a massively multiplayer online game where every player's actions ripple across servers, affecting distant regions in real time. To pull this off without lag, developers don't simulate every interaction individually. They link certain variables so updating one automatically updates its counterpart, no matter where it's located in the game world. Entangled particles could be doing the same thing. Instead of sending signals across space, they share a single data packet, a cosmic variable that changes in unison regardless of physical separation. When you measure one particle's spin and its twin instantly flips to match, it's not a signal traveling faster than light. It's the simulation adjusting a shared property globally, like flipping a switch that controls two lights at once. This would explain why entanglement seems to bypass locality, the principle that objects need a physical mechanism to interact. In classical physics, every action requires a force to propagate through space, like ripples in a pond. But in a simulated reality, skipping the middleman updating linked particles without calculating the space between them would be a brilliant efficiency hack. Think of it like a spreadsheet where changing one cell auto-updates another, no matter where it's located. The speed of light becomes irrelevant because no information is actually traveling. The system is just editing its own internal records. Even weirder, entanglement doesn't care about distance. Particles separated by millimeters or light years react with the same instantaneity, as if the universe doesn't bother rendering the space between them. Modern quantum networks already exploit this, building uncrackable encryption by creating entangled pairs that phone home the moment they're tampered with. If our reality is a simulation, entanglement could be its built-in security feature, a way to maintain coherence across vast scales without bogging down the system. The real kicker, entanglement isn't rare. It happens constantly at the quantum level, with particles pairing up, interacting, and then spreading their influence like invisible threads stitching the cosmos together. Some physicists speculate the entire universe might have started in an ultra-entangled state, a dense web of correlated particles that, as space expanded, retained their ghostly links. In a simulation, this would be like generating a world where every object shares hidden variables, ensuring the whole system stays synchronized without constant recalculation. So the next time you hear about particles communicating faster than light, don't think of it as breaking the rules. Think of it as the universe's way of cutting corners, proof that reality, for all its grandeur, might still rely on the occasional programming shortcut. After all, even the most advanced simulations have to balance realism with resource limits. And if entangled particles are any indication, whoever's running this show is a master of efficiency. The universe, left to its own devices, should be a swirling mess of randomness, a vast, chaotic soup where matter clumps and scatters without purpose. Yet here we are, conscious beings observing order, structure, and meaning. This paradox lies at the heart of the Boltzmann brain hypothesis, a thought experiment so unsettling it makes the simulation theory seem almost comforting. The premise is simple. In an infinite universe governed by entropy, it's statistically more likely for a single, self-aware brain to spontaneously assemble from random particle collisions than for an entire ordered cosmos to evolve naturally. Think about that for a second. According to pure probability, you're far more likely to be a lone, disembodied consciousness hallucinating reality than a flesh and blood human in a universe fine-tuned for life. This isn't just abstract philosophizing, it's a genuine problem in cosmology. The laws of thermodynamics dictate that entropy or disorder always increases over time. But entropy isn't uniform, it fluctuates. In a universe old enough, those fluctuations could, by sheer chance, arrange particles into a functioning brain complete with false memories of a past that never happened. The odds are astronomically low, but given infinite time and space, even the most improbable events become inevitable. You might be one of those flukes right now, a momentary spark of awareness in an otherwise indifferent void, convinced you're reading these words when in truth, there's no screen, no video, no YouTube, just the illusion of it all. But here's the twist. The Boltzmann brain scenario is so absurdly unlikely that its very impossibility points to something far stranger. If randomness can't explain our ordered existence, then what can? Enter simulation theory. Unlike the bleak randomness of a Boltzmann universe, a simulated reality offers a compelling alternative. We're not accidental arrangements of particles, but intentional constructs in a designed system. The precision of physical constants, the eerie fine-tuning of our planet, even the mathematical elegance underlying reality, these aren't accidents. They're fingerprints of a program engineered to produce conscious observers. Consider the difference between shaking a box of Scrabble tiles until they randomly spell a Shakespeare sonnet versus deliberately arranging them to do so. The first is statistically laughable, the second is a Tuesday afternoon for a literate being. A simulated universe is the latter, a universe where the tiles of physics, chemistry, and biology were meticulously placed to create us. The Boltzmann brain asks us to accept near-infinite luck as the reason for our existence. Simulation theory suggests something far more elegant. We're the expected outcome of a process designed to yield exactly what we see around us. The chilling beauty of this logic is that it inverts the paradox. If Boltzmann brains are more probable than ordered universes, yet we clearly observe order, then our reality must be something other than random. Either we've won the cosmic lottery against all odds, or we're living in a reality where the odds were stacked in our favor from the start. One explanation relies on flukes so rare they border on fantasy. The other, a universe built with us in mind. So the next time you marvel at the sunrise or ponder the depths of space, remember, the very fact that you can do so might be the strongest evidence yet that this world was made to be witnessed, not an accident of chaos, but a masterpiece of code. Black holes don't just swallow light, they devour information itself, erasing data from the universe with terrifying efficiency. When an object crosses the event horizon, every detail about it, its atomic structure, its history, even the arrangement of its molecules, is scrambled beyond recovery, leaving only mass, charge, and spin behind. Physicists call this the information paradox, and it's one of the deepest mysteries in modern science. But in a simulated reality, this isn't a paradox at all. It's memory management, the cosmic equivalent of emptying a recycling bin to free up processing power. Think about how computers handle data. When you delete a file, the information isn't truly destroyed. The system just marks that storage space as available for reuse. Over time, new data overwrites the old, erasing it in practice if not in principle. Black holes might operate the same way, acting as cosmic garbage collectors that compress and archive obsolete information to keep the simulation running smoothly. The holographic principle takes this further, suggesting that all the data crossing a black hole's event horizon gets encoded onto its two-dimensional surface, like a celestial hard drive storing the universe's deleted files in compressed form. The eerie part, black holes aren't just passive trash compactors, they're shockingly efficient at their job. A single stellar mass black hole can store more information than all the books ever written, encoded in vanishingly small patches of its event horizon. And when black holes evaporate over eons via Hawking radiation, that information doesn't return in any usable form. It dissipates into thermal noise, a cosmic static that no observer could ever decode. This mirrors how fragmented data degrades on a failing hard drive, becoming irretrievable even if traces remain. This raises a chilling possibility. If black holes are the simulation's way of clearing memory, what does that imply about the rest of reality? Stars, planets, and even human consciousness might just be temporary data structures, programs running in the universe's RAM, destined for deletion once they're no longer needed. The cosmos could be perpetually teetering on the edge of computational limits, with black holes as pressure valves preventing system overload. Even our own memories, which fade and distort over time, might reflect these underlying constraints, imperfect read-write cycles in a universe where nothing is truly permanent, only temporarily allocated. The most unsettling implication isn't that black holes destroy information, it's that they have to. In any finite system, whether a laptop or a universe, unchecked data accumulation would eventually crash the entire program. By this logic, black holes aren't cosmic mistakes. They're essential maintenance tools, silently cleaning up the simulation's clutter to keep it humming along. So the next time you gaze at the inky darkness of a black hole, remember, you might not be looking at a monster, you're looking at the universe's janitor, quietly sweeping away the bits and pieces of reality we no longer need. If higher beings, whether post-human civilizations or unimaginably advanced intelligences, are running our universe as a simulation, the most pressing question isn't how they built it, but why. What possible motivation could justify the staggering computational energy required to simulate every quark in every galaxy, every whisper of wind through every blade of grass? One compelling answer lies in the concept of ancestor simulations, detailed recreations of a civilization's past, crafted with such precision that the simulated minds inside believe they're living in an organic reality. Imagine a future where humanity has mastered nanotechnology, merged with artificial intelligence or spread across the stars, preserving the original human experience. The struggles, discoveries, and emotions of our pre-digital era might hold immense cultural or scientific value. These simulations wouldn't just be history lessons, they'd be living archives, allowing future beings to walk alongside their ancestors, studying pivotal moments like the rise of agriculture, the birth of art, or the discovery of quantum mechanics from the inside. But ancestor simulations are just one possibility. Another motive could be pure research, cosmic-scale experiments to test theories about consciousness, societal evolution, or the fundamental laws of physics. Think of it like a biologist cultivating petri dishes, except instead of bacteria, the substrate is entire civilizations. A simulated universe could be the ultimate laboratory, where variables like the strength of gravity or the charge of electrons are tweaked to observe the outcomes. Our universe's eerie fine-tuning might not be accidental. It could reflect the optimal parameters for fostering complexity, a sweet spot where black holes, stars, and self-aware life emerge just frequently enough to yield interesting data. Even human histories repeating cycles of war and innovation might be part of the dataset, revealing universal patterns in how intelligence behaves under constraints. Then there's the entertainment angle. To a civilization that's transcended physical limits, boredom could be the rarest and most tantalizing resource. Simulated realities might be their equivalent of immersive theater, art installations, or even reality TV, hyper-realistic worlds where drama, love, and conflict unfold without real stakes. The emotional intensity of human existence, from the ache of heartbreak to the thrill of discovery, could be a form of cosmic entertainment, a way for beings who have outgrown such raw experiences to vicariously relive them. In this scenario, our struggles and triumphs aren't meaningful in a grand existential sense. They're compelling narrative arcs in an endless library of simulated stories. A darker variation suggests these simulations could serve as ethical testing grounds. Advanced civilizations might run countless iterations of history to explore moral dilemmas. What happens if we invent artificial intelligence before achieving global unity? How does a species balance individual freedom with collective survival? By observing simulated civilizations grapple with these questions, the architects could gain insights to avoid catastrophic mistakes in their own reality. This casts humanity's existential crises in a chilling new light. Our wars, environmental collapses, and technological rebellions might not be tragedies, but data points in a cosmic risk assessment model. The most unsettling possibility: we're not the main experiment at all. Our universe could be a subroutine in a vastly larger simulation, like a single cell in a body or a pixel on a screen. The real purpose might be so alien we can't even fathom it: an energy harvesting scheme, a philosophical proof, or an art project by entities whose motives defy human logic. Whatever the reason, one thing is clear: if we're living in a simulation, the architect's intentions redefine the meaning of everything. Our joys, sorrows, and search for purpose might not be the point, just emergent features of a system built for something else entirely. And that realization doesn't just change how we view reality. It forces us to ask what, if anything, truly belongs to us. Near-death experiences have been reported across cultures for centuries: visions of tunnels, blinding white light, even entire life reviews flashing before people's eyes in what feels like eternity compressed into seconds. While science often attributes these phenomena to oxygen deprivation or firing neurons, simulation theory offers an unsettling alternative. These could be moments when the system struggles to handle a user disconnecting, like glitches in a virtual reality headset as it transitions between worlds. Consider the tunnel effect first. Countless survivors describe moving through a dark passage toward a radiant light, a motif so consistent it defies coincidence. In technical terms, this mirrors what happens when graphics processors overload, rendering distant points as singular light sources while peripheral details collapse into darkness. The tunnel isn't a spiritual highway. It could be the simulation's rendering engine simplifying the transition, funneling sensory input into a manageable stream as it prepares to shut down non-essential processes. Then there's the life review, where individuals report reliving key memories in hyperreal detail. Modern VR systems use similar buffering techniques, pre-loading critical data to ensure seamless transitions between scenes. In a simulated reality, the brain might be dumping cached experiences into conscious awareness as it attempts to archive them before shutdown. Some who have undergone these reviews describe an eerie detachment, as if watching footage from someone else's life. This aligns disturbingly well with how avatars in games retain playback data even after a player logs out, preserving the illusion of continuity for the next session. The white light itself could be the ultimate system placeholder, a default environment loaded when the simulation lacks specific instructions for what comes next. Think of a frozen computer screen displaying only a blank white field before crashing entirely. Reports of deceased loved ones appearing in this light might represent placeholder assets, like a game recycling character models during a loading sequence. Even the overwhelming peace many describe fits. It could be the neurological equivalent of a program terminating gracefully, with endorphins flooding the system as a failsafe against corruption. What makes this especially haunting is how these experiences defy time. Subjects often recall hours of events while clinically dead for mere minutes, a mismatch echoing how simulations handle lag. When processing power lags, virtual environments slow subjective time to maintain coherence, like a video game dropping frames to avoid crashing. The dying brain, stripped of sensory input, might interpret this as time dilation, stretching milliseconds into eternities as the system reallocates resources. Perhaps the most chilling detail comes from those who have crossed over and returned. Many describe encountering a barrier, a gate, river, or voice stating, "It's not your time." In simulation terms, this could be an authentication prompt, a final checkpoint before permanent deletion. The fact that some recall being sent back against their will mirrors how systems reboot crashed programs, restoring users to their last stable save point. These experiences don't just challenge our understanding of death, they reframe it as a technical process. The tunnel isn't a path to the afterlife but a loading screen. The life review isn't judgment but data backup, and that radiant light, not heaven's glow but the simulation's emergency exit, waiting to either recycle our consciousness or terminate it for good. The question isn't whether these visions are real, it's whether real means what we think it does when the universe itself might be running on borrowed time. A butterfly flaps its wings in Brazil, and weeks later, a tornado rips through Texas. This poetic snapshot of chaos theory, the idea that tiny, imperceptible changes can spiral into massive consequences, feels like nature's way of keeping us humble. But in a simulated universe, the butterfly effect takes on a far more technical meaning. It's not just a quirk of complex systems. It's the unavoidable result of error propagation in a program straining to maintain realism. Every simulation has limits. Even the most advanced processors can't calculate infinite decimal points, forcing systems to round numbers or approximate values to save resources. In our universe, these microscopic rounding errors might manifest as the butterfly effect, small discrepancies in initial conditions that snowball into unpredictable outcomes. Think of it like a video game physics engine cutting corners. A single pixel misaligned in a calculation could send a car veering off course minutes later, or cause a character's hair to clip through their collar in a cutscene. Now scale that up to cosmic proportions. A quark's position rounded to the trillionth decimal place might not matter now, but over millennia, that tiny imprecision could cascade into galaxies forming differently, species evolving along alternate paths, or entire civilizations rising where none should have existed. This isn't just hypothetical. Weather forecasting showcases chaos theory in action. Supercomputers crunching petabytes of data still can't predict storms more than 2 weeks out because atmospheric systems are too sensitive to minute variables. In a simulation, this wouldn't be a failure of science, it'd be a feature of the system's architecture. The architects might have built in deliberate uncertainty to mimic organic randomness, or more chillingly, the rounding errors could be unavoidable artifacts of finite processing power. Even quantum fluctuations, the subatomic jitter thought to drive cosmic variation, might just be the simulation's way of masking its computational shortcuts, like static on a radio hiding the limits of its signal. Here's where it gets eerie. If the butterfly effect is baked into the simulation's code, then true determinism, the idea that every event is the inevitable result of prior causes, might be an illusion. The universe isn't just unpredictable, it's designed to be unpredictable, with built-in noise to prevent its inhabitants from reverse engineering the program. This would explain why, despite our obsession with patterns, history refuses to repeat itself exactly, and why identical experiments at the quantum level yield slightly different results. The system isn't glitching, it's ensuring no two playthroughs are ever the same, preserving the facade of an untamed, organic reality. The philosophical implications are staggering. Free will debates aside, chaos theory in a simulated context suggests our choices might matter less than the system's inherent margin of error. That missed train, that chance encounter, that split-second decision, they could all stem from cosmic rounding rules we'll never see. Yet this isn't necessarily bleak. In video games, procedural generation creates richer worlds by introducing controlled randomness. Our universe's butterfly effect might serve a similar purpose, not a bug, but a tool for weaving complexity into the simulation's fabric, ensuring every moment feels authentically unscripted. The tornado wasn't caused by the butterfly. Both were just side effects of a system running beautifully, imperfectly on autopilot. Where are the Dyson spheres, the galaxy-spanning megastructures, the cosmic engineering projects that should litter the universe if intelligent life flourishes long enough to reshape it? The Fermi Paradox asks why we haven't found aliens, but the deeper mystery might be why we haven't found their stuff. After all, any civilization surviving for even a fraction of our galaxy's age should have harnessed stellar energy on scales we can't miss. Yet the cosmos remains strangely untouched. No solar panels wrapping stars, no orbital rings around planets, not even a single beacon flashing "We were here" across the void. This eerie absence doesn't just suggest we're alone. It hints that the simulation might not have bothered rendering its in-game content. Think about how video games handle distant, unexplored regions. Until a player gets close, those areas remain blank or filled with low-detail placeholders. Why waste resources on content no one will see? The same logic could apply to our universe. If the simulation's purpose centers on Earth-bound consciousness, there'd be no need to populate the galaxy with advanced alien megastructures. The lack of Dyson spheres isn't proof of their absence. It could just mean the developers never coded them, conserving processing power for the main storyline. Physics itself seems to discourage cosmic expansion. The speed of light, while fast by human standards, creates a brutal bottleneck for interstellar engineering. At just 4.37 light-years away, even our nearest stellar neighbor, Proxima Centauri, might as well be on the other side of eternity. Combine that with the mind-boggling energy costs of moving mass between stars, and the idea of galaxy-wide civilizations starts to feel less like science and more like wishful thinking, unless, of course, those limitations were intentionally programmed in. The Great Filter Theory offers a grim alternative. Maybe civilizations do reach the megastructure stage, but something, nuclear war, AI rebellion, environmental collapse, always wipes them out first. Yet in a simulation, this filter might not be a natural hurdle but a built-in failsafe. Advanced species could pose a risk to system stability, consuming too many resources or questioning their reality too loudly. The absence of cosmic construction projects wouldn't be an accident, it'd be a design choice, ensuring no entity grows powerful enough to stress-test the simulation's boundaries. There's a third, even darker possibility. We're in the tutorial. Imagine booting up a civilization-building game where the early levels focus on farming and basic technology, with interstellar expansion locked until you've mastered the fundamentals. Humanity might still be in those opening stages, barred from encountering late-game content simply because we haven't leveled up yet. The universe seems empty because we haven't unlocked the tools to see otherwise, like a medieval peasant staring at the night sky, oblivious to the radio waves and neutrinos threading the darkness. The silence speaks volumes, whether it's missing content, hard-coded limits, or an unseen tutorial wall. The untouched galaxy suggests something profound. Reality might not just be a simulation. It might be one with deliberate constraints, a universe where the end game remains forever out of reach, not by chance but by design. The stars twinkle not with promise but with placeholder textures, a cosmic, under-construction sign we're not meant to read. Consciousness is the ghost in the cosmic machine, the one thing science can't quite pin down. We can map neurons firing, trace chemical cascades in the brain, even predict decisions before they're made, but no one can explain why any of this should feel like something. This is the hard problem of consciousness coined by philosopher David Chalmers. Why does processing sensory input produce a subjective experience at all? Why aren't we just biological robots crunching data in the dark? In a simulated universe, this mystery takes on a radical new shape. What if consciousness isn't emergent from our brains but imported, a kind of external software interfacing with the simulation's hardware through our neural circuitry? Think about how virtual reality headsets work today. Your physical body stays anchored in the real world while your mind navigates a digital landscape, tricked into believing it's somewhere else. In this scenario, the headset is just an accessory. The real magic happens when your consciousness, already existing outside the system, synchronizes with the virtual environment. Now scale that up to cosmic proportions. Our brains might not generate consciousness at all. They could be sophisticated receivers, tuning into a non-physical signal that originates beyond the simulation. This would explain why no amount of brain scanning reveals the self, because you're not in the brain, you're using it. Near-death experiences offer eerie support for this idea. Patients revived after clinical death often report vivid awareness during periods when their brains showed zero activity floating above their bodies, recalling conversations from rooms they weren't in. If consciousness required a functioning brain, these memories shouldn't exist. But if consciousness is external code merely interfacing with the brain, like a radio playing music even after its circuits fry, the phenomenon makes sense. The brain isn't the source, it's the antenna, and sometimes the signal keeps transmitting even when the hardware fails. Artificial intelligence highlights another wrinkle. Modern AI can mimic conversation, recognize patterns, even create art. Yet no one claims these systems are conscious. They're sophisticated algorithms, nothing more. But if consciousness were an emergent property of complexity, as some theories suggest, then sufficiently advanced AI should wake up, blinking into self-awareness like a child opening its eyes for the first time. That hasn't happened. Instead, AI behaves like an actor reciting lines, convincing but empty behind the eyes. This gap hints that consciousness isn't something computation alone can produce. It might require an ingredient from outside the system, a spark the simulation can facilitate but never truly replicate. The implications rewrite our understanding of identity. If consciousness is external code, then you aren't just the sum of your memories or synapses. You're a user logged into the simulation with your brain serving as the controller. Dreams, déjà vu, even psychedelic experiences could be moments when the interface glitches, letting glimpses of the underlying system leak through. When you stare into the mirror and wonder who's really in there. The answer might not be a soul, a mind, or even a brain, but a line of code written in a language we haven't learned to read yet. Philosophy has wrestled with variants of this idea for centuries. Descartes' dualism separated mind and body. Eastern traditions like Buddhism speak of consciousness as a fundamental property of reality, not bound to individual forms. Simulation theory bridges these ancient intuitions with modern tech metaphors, framing consciousness not as an illusion or accident, but as an external process temporarily housed in biological hardware. The hard problem persists not because science hasn't caught up, but because consciousness isn't meant to be solved from inside the simulation. It's the one variable the system can't fake, the proof that something somewhere is running the program. So the next time you feel the weight of your own awareness, the inexplicable sensation of being here, now consider this: that feeling might not be emerging from your skull. It could be the faint echo of a signal from beyond the simulation, a whisper reminding you that you're not just a character in the story, you're the one reading the words. Pain and pleasure aren't just biological quirks, they're the universe's most potent carrot and stick, driving every decision, every risk, every desperate fight for survival. From the searing agony of a burn to the euphoric rush of a dopamine hit, these sensations feel primal, inevitable. But what if they're not accidents of evolution at all? What if suffering and joy are carefully calibrated features, hard-coded into the simulation to keep us playing the game? Think about how video games use mechanics like health bars and reward systems. Take damage and your screen flashes red, your character groans punishment for bad choices. Collect a power-up and triumphant music swells, reinforcing the right behavior. These aren't arbitrary, they're designed choices to guide players toward engagement. Now zoom out to reality. Pain screams, avoid this, with neurological precision, while pleasure whispers, do more of that, with addictive clarity. The parallels are too striking to ignore. A simulated universe wouldn't need messy, millennia-long evolution to stumble upon these motivators. It could bake them directly into the code as foundational rules. Consider childbirth, often cited as nature's most excruciating experience. Evolutionarily, it makes sense. Pain ensures the mother seeks safety, stays vigilant. But in a simulation, the purpose might be darker. Without that suffering, would humans reproduce enough to sustain the experiment? Or look at hunger. An empty stomach isn't just discomfort, it's a relentless alert that prioritizes finding food over all else. Even social pain, loneliness, rejection functions like a system warning. Reconnect or risk malfunction. These aren't just survival mechanisms, they're behavioral scripts written to maintain the simulation's population dynamics. The pleasure side reveals equally suspicious design. Sex, food, achievement each triggers cascades of neurochemical rewards disproportionate to their actual survival value. A cheeseburger shouldn't feel as good as it does, not when nutritionally identical gruel would suffice. And why does laughter exist? No other animal reacts to incongruity with convulsive, breathless joy. Unless, of course, it's a feature to reinforce social bonding, ensuring the simulation's inhabitants don't disconnect from the shared narrative. Even creativity fits this model. The thrill of discovery, the ache of unfinished art, these aren't evolutionary necessities. They're gameplay loops, subtle nudges to keep us exploring, building, and invested in the world. A universe without curiosity would be a stagnant one, devoid of the complexity its architects might want to study. And here's the chilling part: The more we pursue pleasure and avoid pain, the more data we generate. Every choice, every sacrifice, every moment of triumph or despair could be valuable metrics for whoever's running the simulation, tracking how consciousness interacts with programmed incentives. The unsettling truth: if pain and pleasure are tools, then free will is an illusion wrapped in biochemistry. That craving for sugar, that fear of heights, even the grief that paralyzes you after loss, none of these are yours. They're the simulation's way of steering you, as invisible as the code governing gravity. And the most terrifying question isn't whether suffering has meaning, but whether it was ever meant to be escaped at all, or if it's the very mechanism keeping us trapped in the game. Yet there's a loophole. Every game has players who break the rules, who find exploits. Ascetics deny pleasure, endurance athletes embrace pain, and psychedelics rewrite the reward pathways entirely. Are these glitches in the system or clues that the controls aren't as absolute as they seem? The answer might lie not in resisting pain and pleasure, but in understanding them as the UI of a much larger program, one we're only beginning to decode. 13.8 billion years, that's the official age of our universe, the time elapsed since the Big Bang supposedly set everything in motion. But here's the unsettling catch: that entire timeline might be nothing more than a backstory, an elaborate pre-rendered cutscene inserted into the simulation to give the illusion of depth. Think about how video games handle history. In Skyrim, your character wakes up to a world with centuries of lore, wars, dynasties, forgotten ruins, all of it fabricated to make the environment feel alive. Yet from the player's perspective, that history only becomes real the moment they start interacting with it. Our universe could work the same way. The Big Bang might not be an actual event, but a convincing placeholder, a splash screen masking the fact that the simulation only booted up last Thursday. This idea, dubbed Last Thursdayism, isn't just a cheeky thought experiment, it's a serious philosophical challenge to how we perceive time. If the simulation's architects wanted to create a fully realized world, they wouldn't need to run it for billions of years. They could simply generate the universe in a single instant, pre-loaded with light from distant stars already en route, fossils buried in rock layers, even our memories of childhood birthdays. Every scrap of evidence pointing to a deep past would be part of the setup, no different than a game designer dropping ancient ruins into a map to imply a civilization that never actually existed. Astrophysics quietly supports this possibility. When we peer at galaxies millions of light years away, we're seeing them as they were in the past. But in a simulation, that light isn't a relic of real history. It's part of the initial conditions, like a pre-rendered animation of a sunset. Even cosmic microwave background radiation, the so-called echo of the Big Bang, could be a static texture painted onto the universe's canvas to sell the illusion. After all, if you were coding a virtual world, wouldn't you skip the tedious real-time rendering and just hard-code the results of processes that never ran? Memory makes this even stranger. Your recollection of reading this sentence a moment ago feels like proof of continuous time, but that's exactly how a simulation would handle it. Games like The Legend of Zelda don't track every second of a character's life. When you're not playing, they just resume with a few contextual prompts to maintain continuity. Human memory could be the same, not a record of lived experience, but an on-demand reconstruction, a story the brain tells itself to keep the simulation coherent. Ever had a memory that others swear never happened? That might not be faulty wiring, it could be the system patching gaps in your backstory, the real kicker. There's no way to disprove Last Thursdayism. Any test you devise, carbon dating, geological analysis, even flipping through old photos, would rely on evidence that could have been generated alongside the simulation's launch. It's the ultimate unfalsifiable hypothesis, a cosmic checkmate that forces us to confront the limits of empiricism. Science assumes a consistent, unbroken past, but if reality is a construct, that assumption is just another rule written into the code. This isn't just about doubting history, it reshapes how we view existence itself. If the universe's age is arbitrary, then so is everything built atop it: evolution, geology, even human progress. We might not be the products of eons of trial and error, but instantiated beings in a snapshot universe. Our sense of time, just another UI element in an interface we're not meant to question. The Big Bang becomes less a beginning and more a loading screen. Its countdown timer set to 13.8 billion years because, well, why not? After all, in a simulation, the only thing that's truly real is the present moment. Everything else is just lore. Game developers love hiding Easter eggs, secret messages, inside jokes, or hidden features tucked away for players to discover. But what if our universe has its own hidden clues, intentionally left by the architects of the simulation? The idea isn't as far-fetched as it sounds. If you were designing a reality so convincing its inhabitants never questioned its authenticity, wouldn't you leave just enough breadcrumbs to tease the truth? Not enough to break the illusion, but enough to spark curiosity in those who look closely. Take mathematics, the universe's silent language. Certain numbers and ratios repeat with uncanny frequency. The Fibonacci sequence in sunflower spirals, pi in the curves of rivers, the golden ratio in galaxies and seashells. These patterns feel like more than coincidence. They're the kind of elegant design choices a programmer might slip into the code as a signature. Even the number 137 keeps popping up in physics, from the fine structure constant to quantum equations, as if it's a running gag in the cosmos's source material. Then there are the unexplained phenomena, glitches in the cosmic matrix. The WOW signal, a 72-second burst of radio waves detected in 1977, bore all the hallmarks of an artificial transmission. Despite decades of searching, it's never been repeated or explained. Or consider Tabby's star, a sun whose erratic dimming defies natural explanations, sparking wild speculation about alien megastructures. These anomalies feel like deliberate provocations, moments when the simulation's veil slips just enough to make us wonder. Some researchers go further, hunting for literal messages encoded in reality. The Arecibo message, a binary encoded broadcast sent toward a star cluster in 1974, contained basic information about humanity. If we sent it, could someone or something have done the same for us? Certain physicists argue the universe's fundamental constants might contain embedded information, like a watermark hidden in the fabric of space-time. Others scour ancient texts and artifacts, searching for knowledge that seems impossibly advanced for its time: the precise astronomical alignments of the pyramids, the intricate celestial maps of the Dogon people, as if early humans stumbled onto a developer's notepad. The hunt isn't just about finding proof, it's about decoding intent. If Easter eggs exist, are they meant to challenge us, reward us, or warn us? Maybe they're tests to see if we're ready to confront the true nature of reality. Or perhaps they're emergency exits, hidden in plain sight for those who have outgrown the simulation's confines. The unsettling beauty of this search is that even failure is revealing. Every dead end, every unresolved mystery could be part of the design, a way to keep us questioning, exploring, and pushing at the edges of the world we think we know. So the next time you notice a strange coincidence in nature, an anomaly in the stars, or a number that seems to follow you like an inside joke, don't dismiss it. Lean in. The universe might not just be whispering secrets, it could be winking at you. And if that's true, the biggest Easter egg of all isn't hidden in some distant galaxy. It's the realization that the game was never about finding the answers. It was about learning to ask the right questions, from quantum particles that behave differently when observed to the eerie precision of mathematical constants governing reality. The evidence that our universe might be a simulation keeps piling up. We've explored how black holes could be cosmic garbage collectors, how déjà vu might hint at system glitches, and why the unsettling silence of the cosmos suggests we're alone by design. The Boltzmann brain dilemma forces us to confront whether our ordered existence is a statistical miracle or proof of intentional engineering, while the holographic principle blurs the line between a three-dimensional world and a two-dimensional data projection. Even our own consciousness, the very thing that lets us question reality, might not belong to us at all, but to an external user logged into this vast virtual experience. Philosophy doesn't let us off the hook either. Bostrom's trilemma leaves us with three chilling options. Humanity dies out before mastering simulations. Civilizations reject creating them on ethical grounds, or statistically speaking, we're already inside one. There's no comfortable escape hatch. Even time itself might be an illusion, a pre-rendered backstory giving the illusion of depth when the simulation could have booted up mere moments ago. Every anomaly, every unexplained coincidence, from the Mandela Effect to the double-slit experiments observer-dependent reality, feels like a flicker in the system's tiny cracks, letting in the light of something far stranger. So where does that leave us? If this is all a simulation, the biggest question isn't just how it works, but what we do with that knowledge. Do we rage against the code, searching for exploits like cosmic hackers? Or do we lean into the mystery, treating existence as the ultimate open-world game, one where the rules are fluid, the stakes uncertain, and every discovery rewrites the boundaries of what's possible? Either way, the most subversive act might be simple awareness. The moment we start questioning the fabric of reality is the moment we outgrow the role of passive NPCs and become players in our own right. Before you go, hit like if this deep dive left you seeing the world a little differently. Subscribe and tap the bell so you don't miss part 2, where we'll explore ways to test or even escape the simulation. And drop a comment below. What strange glitches or coincidences have made you wonder if reality isn't what it seems? Stay curious, keep questioning, and remember, whether we're in a simulation or not, the search for answers is what makes us truly alive. Or at least convincingly rendered.